Hello. Today I'm going to quickly take you through how to use PCTE's script for imaging CoroMap data inside R. The CoroMap is a tool used to measure the half-cell potential, the resistance along the circuit, and the corrosion rate of reinforcing steel in concrete. Because it uses a direct connection to the reinforcing steel, its measurements are directly related to the corrosion occurring to that steel and are not a correlated measurement. The R project is a programming language and environment for working with data for statistical computations and graphing. And in this particular case, we're using its graphing components to very quickly produce the final heat maps and contour maps from a set of CoroMap data. Because the script we've prepared also imports the data into the R environment, you have the ability to go out and do your own statistical analysis and to improve upon what we've written, but this is a good starting point that produces a very clear image. We've created the R code inside RStudio, which is an integrated development environment for R, and is a very convenient way to edit and run R code. So the script for R is used to create images for the half-cell potential measurements, the resistance, and the corrosion rate from the raw data from a CoroMap. When you open a new file in the CoroMap and you take a measurement, these measurements are stored in a .txt file every time a measurement is taken. If you go and then finalize that measurement, a .csv file is created, which is intended for import into other software. For the purpose of this script, we're going to be using the raw data, which is the .txt file. The script that has been prepared will extract individual measurements for half-cell potential, resistance, and corrosion rate. At this point in time, it does not take out the annotation data, nor does it take out the individual graphs created while a galvanostatic pulse is applied to measure the corrosion rate. The script then, once it's extracted this data, prepares a heat map with contour lines for the half-cell data, the corrosion rate, and the resistance. There are parameters at the beginning of the script that allow a user to edit the color of these charts, to edit the scale of these charts, and those will remain fixed for any other files loaded, and to also change how many contour lines appear upon a set of data. In order to use the script, the user will have to install the R project runtime environment, and because we've worked inside RStudio, I'm going to be showing how to run this script inside RStudio. So once these two are loaded, you may then go onto PCTE's website and download the CoroMap script, which contains the .r file with the script in it. It also contains a more detailed README that takes you through in a little more detail than I'm going to show you today how to install and run the data. So once you have installed RStudio and downloaded the script from our website, you will have two files inside there. As I mentioned, the README file has full instructions on loading the script into the software, how to adjust the parameters, and how to produce an image. For the sake of, I'm going to show you quickly these same steps now, so you have a visual reference of the same task. So to begin, you need to start RStudio, and you need to load in the CoroMap script. So if you go into Open File and navigate to the CoroMap-v1.r file and open it, the script will appear in the top left pane of your RStudio window. And if you have a look at this script, you can see that it shows the configuration, where we can tell which folder and which file is being worked upon. We can set the parameters for number of contour lines, and also the way the colors appear, and what the limits are on the color scales for each chart. Finally, the actual script will take these values and perform the operation. Now, a quick warning, the very first time you run this script, it may need to take 15 to 20 minutes to install what is called the Tidyverse package, which is an extension to R used for graphing and imaging. So this will happen automatically, but if it starts bringing up downloading files, installing files, that's what's happening. Tidyverse is being installed. After that, the code will extract the data from the .txt file and prepare it for work, removing any outliers and duplicate data, and then it will chart each image. So step by step to load a file into this script, we first need to adjust the path. The default is to a folder called core.test, and it is listed as /core.test. This / refers to the documents folder on a Windows computer. So if we open the documents folder, I have inside that folder the core-test folder, but I could use any folder inside here. To show you what the / folder format actually corresponds to, we can see here that it is everything up until documents is represented by that /. This is a default setting. It may change if you do edit it in RStudio, but this is where the default is. Inside that, I have two specific files from a Cora map. I've got sample and sample2 here. I can tell that these are .txt files by their type. Alternatively, on a Windows computer, if you want to see the file extensions directly, you can go to Folder and Search Options and turn off Hide Extensions for Known File Types. And now the file extensions are visible. So in this case, I'm going to image sample2.txt. So I can take the folder I'm working in, which corresponds correctly, and then I need to take the file name I'm working in. So this would be sample2.txt. So now I've told it which folder and which file. Please be aware this is case sensitive, and once you've done this, the next step should be to use the source button to run the script. When you press the source button, everything in the left screen will run. So we're going to see some activity down here in the console. Don't worry if you see any warnings or errors in here, because what we're concerned with is that the images appear correct on the right-hand side once the run is complete. So I have here a graph for corrosion rate, but I know this data was not collected with corrosion rate, so grey is fine. This just means there's nothing in that particular section. But we also have a resistance graph showing regions from red to green, so greater than 100 is going to appear as grey because our highest value is 100 and our lowest value is red. And also for our half cell potentials, we can see again we've scaled from red to green, but we've actually got some grey sections where we're outside the minimum or maximum on that scale. So we need to fix that first. So the first step is going to be to adjust our configuration for colors. So we know we're that we're too short on either bound. So if I change this from positive 100, so towards negative 600, say, I should now remove some of these grey portions on the half cell potential graph. So I'll rerun the data. And when I come back to my half cell data, we now see that we go from a red to a green. Maybe that's minus 600 was a little bit too far, so I'll bring it back to 500. Press the source button again to recreate the plot. And now my half cell data is looking pretty good. There's a couple of grey spots, so maybe 550. And that's a pretty good graph of half cell potentials in this region. And the interesting thing we can see here is the correspondence between the very positive half cell values in a region of quite high resistance, high enough to indicate that there in fact may be a delamination or separation on the concrete there. Again, we can adjust the scale to better cover this, but if there is a infinite resistance essentially, or no resistance can be measured, it's still going to appear as grey. So that's a little bit better, but it shows just how high the resistance is around this lower region. So if I was looking at this in terms of half cell data, I'd be pretty reluctant to interpret this directly because of the discontinuity indicated by that resistance. We can also adjust the colors. This is based upon a set of code words for different colors. So if I just change this, say, to red and green rather than the specific names, we're going to get a slightly different color scale here when we run. This is a little bit brighter, a little more traditional scale there. The other thing we can do is we can adjust our bin width, so we can actually see there's a lot of contours over this. If we want to have less contours, we could maybe make them appear every 100 units, which is going to, so this will halve the number of contours that appear on that graph for half cell potential. So this is the basics of using the scripts to load a data file. If I want to load another file, I can simply change the file here. So the other file I had was called sample. So now when I run this one, we're going to get a different chart. In this case, we can actually see there's not much difference in color scale, so I want to cut these down a bit. So maybe minus 400 to 0 would be a good scale for this half cell data. So we'll try again. And that's quite a bit better. That gives us a clearer visual towards that value here. So once we're happy with the graph, you can export any of the individual images. Let me see, we've got actually some corrosion rate data on this file because there was a couple of measurements taken about one point. But any of these images can be exported as an image, as a PDF, or copied to the clipboard. I'm going to just choose export as image. I can choose the image type, where it's going to be saved, change the file name. I can also change its size, so it's currently pretty small. So if I want a bit wider, I can choose my size into one that's suitable for the report I'm going to be creating. So that's pretty nice. And then save the image. And that's the final result. So you can see you can very quickly work through a whole set of data from a CorelMap project. Thank you very much for listening. If there's anything more you'd like to know about the script or R in particular, there's a lot of useful tutorials about R in general. And I'd be very happy to answer any comments below about the script itself. Thank you very much.